Okay, everyone, welcome back to CPEE 517 WS Digital and Computer System Architecture. This is lecture 2 of part 2 of lecture 5, memory access time. So if you remember at the very beginning, we talked about this, right? So we said there's a gap between processor and memory access performance, both latency and throughput. So what we're going to do is we're going to use a bridge, some buffer between CPU and main memory to sort of, to mitigate this gap. Why? First, this cache is faster. The main memory is like a orders of magnitude, typically 1 to 2 orders, like 10 times to 100 times faster than main memory, okay, in terms of latency. And then, however, the cache is faster because it's small, right? Imagine to find a single atom from a set of 2 elements versus a set of 2 billion elements. Clearly, finding one element from a set of 2 is faster than a set of 2 billion. So the population matters. So cache is typically smaller than main memory, right? And that's the thing we have to keep in mind. Second, definitely, as what we mentioned before, cache use SRAM. Well, main memory use DRAM cell. So SRAM does not need a refresh, and also it's faster. Okay, that's the 2 typical reasons why cache is faster. So first is small, second is using better materials. Well, when cache is small, it means cache cannot contain all the data from main memory, right? You have 2 billion elements, while cache can only cache 2. So that means some part of the main memory cannot be in the cache. Then we have to use locality to better cache the data of interest. Well, since cache cannot hold all the data of our interest, then there's miss rate and hit rate. This is a very important term. You guys have to remember that. So first, hit rate means the fraction of the access that found the data of interest in cache. It's high. It's so high such that it goes beyond, I think, 95%, 99% typically. That's why we typically focus on miss rate, like the time, the occurrence that your data you want to access, that data is not in cache. Why? Because of locality. Okay, the power of locality is a lot. So average memory access time then becomes the hit time, like the time you hit in cache, plus the miss read, multiply the miss penalty. Like a miss penalty could be you first have to refer to cache, and then it's not there, and then you have to go to the memory. Main memory probably is also not there, so then you have to go to what? Disk, right? Secondary storage. The miss penalty includes the time to replace a block from the lower level, including time to replace in CPU, the access time to the lower level equals the latency to lower level, and transfer time, the time to transfer the block from the lower level to the upper level or the cache. Okay, so basically the miss penalty includes the time to replace a block in the CPU. It includes the access time, the time to the lower level, and the transfer time, right? So that's the miss penalty. We're gonna have a very detailed exercise on this. Here. Assume CPI is 1.0 when all memory accesses hit in the cache. The only data accesses are loads and stores, accounting for 50% of the instructions. The miss penalty is 25 clock cycles, and the miss rate is 2%. How much faster would the computer be if all the instructions were cache hits? Please use 15 minutes to solve this problem. The two equations you need to use is CPU time and memory clock cycle. Pause the video for 15 minutes, solve it, and then look into the answer, okay? Thank you. All right, so here's the case. The memory access time equals IC multiply 1 plus 0.5 multiply 0.02, which is the miss read, multiply 25, right? So it equals IC multiply 0.75. Then the new CPU time versus the old CPU time is 1.75. So that means even we only have 2% of the miss read because the penalty is very large, right? Very high, 25 clock cycles. Then you can see 1.75 times slow down. Or if you get it faster, it's like 1.75 times faster, right? Just by removing 2% of the miss read. Okay,